Hello everyone and welcome to Robot Operating System version 2 or ROS2 Jazzy tutorials. In this ROS2 Jazzy tutorial, we explain how to write a Python program and a ROS2 package from scratch that demonstrate how to implement all the components of an algorithm, or better to say a controller, for controlling the position of a mobile robot in 2D space. Over here, you can see an illustration of a mobile robot in 2D space. Here are the wheels, wheel 1 and wheel 2, and here is the robot body. By changing the velocity of the two wheels, we can control the position and orientation of this robot in two-dimensional space. Our goal, or better to say our control assignment, is to steer the robot from this position B to the desired position D, represented over here. That is, we need to design the algorithm that will adjust the orientation and position of the robot such that the robot goes from the point B to the point D. To implement the control algorithm and to investigate its behavior, we are going to use ROS2 Jazzy Jalisco and the Turtle Sim simulation shown over here. Namely, a mobile robot is represented by this turtle over here. The turtle can move in the two-dimensional plane. It can rotate and it can also move along the straight line in the local coordinate system. The control assignment is to steer this turtle from the starting position, that is from the center, to any point inside of this plane. Over here, you can see the coordinates of the desired point. Namely, we want to steer the turtle to the x coordinate 0.5 and the y coordinate 8. So let's see how this thing works in practice. Namely, in this terminal, I will build the package, and in the terminal shown over here, I'm going to run the node. First, let's leave this window open, and if I run this command, the turtle will move. And you can see how the turtle moves to the desired position. Looks really good. Now, let's stop the control algorithm and let's change the coordinates. For example, let's steer the turtle to 0.5, 0.5. Let's save the code. Then let's again go to the terminal, build everything, and then over here, let's run the code once again. And over here, you can see how quickly turtle moves to the desired position. In this video tutorial, we explain how to write this Python code that implements the algorithm in Python and ROS2 Jazzy Jalisco. You can see that the control algorithm is implemented inside of a class. In addition to this code, you're going to learn how to write a ROS2 package from scratch. We have created a manual that thoroughly explains all the steps that you need to perform in order to implement the control algorithm. And here's the manual. The manual has 9 pages. The code, this manual, and the complete ROS package will be posted in the description below this video tutorial. That is, links to all the files explained and used in this video tutorial will be posted in the description and in the comment section below this video tutorial. Before we start with the explanation, here's the license and the copyright notice. This document develops code files, lesson video, and all the provided material are referred to as the learning material in the sequel. The learning material is the ownership and the original work of Dr. Alexander Haber, who is referred to as the author in the sequel. You have the right to use the learning material for personal educational use and strictly for non-commercial use. The learning material should not be copied, redistributed, or publicly posted on public or private websites, code repositories, and social media platforms. The learning material should not be reproduced manually or automatically using an algorithm or an AI model from this video and then posted on public or private online repositories. Unless allowed by the author, the learning material should not be used as lecture material on online learning platforms and in university courses. Unless allowed by the author, the learning material should not be used to organize courses for training engineers working in companies or paid academic researchers, that is, paid students, paid postdocs, paid professors, etc. The provided code files and learning materials should not be used to train an AI algorithm or a large language model. And finally, unless allowed by the author, the learning materials should not be used to produce academic papers, student reports, or other documents. Okay, so let's start with implementation. To implement the material presented in this tutorial, you need to have Linux Ubuntu 24.04. Do not use Windows Subsystem for Linux or WSL since you might have issues displaying graphics. Install Linux Ubuntu on a computer. If you have a Windows computer, then you can install Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. Let's verify that you have the correct Linux distribution. Click here, then search for terminal. Then over here in the terminal you need to write a single command. Here is the command. And if you see Ubuntu 24.04, you can proceed watching this video tutorial. If not, then install Linux Ubuntu 24.04. Then you need to have a ROS2 Jazzy Jalisco distribution installed on your system. If you don't have this particular ROS2 distribution, then go to my YouTube page and there is a tutorial explaining how to install ROS2 Jazzy Jalisco on Linux. Simply search for install ROS2 Jazzy Jalisco and there are two tutorials. Let's verify that you have properly installed ROS2 Jazzy Jalisco. To do that, execute this command. This command is going to list the content of this folder. Namely, this is the standard installation folder for ROS2 Jazzy. And if this folder is non-empty, as it is in my case, then most likely ROS2 Jazzy Jalisco is properly installed on your system. However, we still need to perform additional verification. One very important verification is to try to execute setup.bash file from the installation directory. If you can install or actually execute this file with no errors, as I did, then most likely ROS2 Jazzy is properly installed. And as the final verification, let's print this environment variable. And if you see Jazzy, then congratulations, ROS2 Jazzy Jalisco is properly installed on your system and we can continue further. The next step is to install and start TurtleSim node and simulation and get yourself familiar with TurtleSim. The first step, as always, is to create an underlay. The underlay is a basic ROS2 configuration and a set of parameters created and defined by sourcing a setup script provided by the standard ROS2 installation. The underlay provides the necessary build dependencies, libraries, and packages necessary to execute the ROS2 commands and build packages using the Colcon build system. We have already created an underlay in this terminal by sourcing the standard setup.bash file. However, in order to practice sourcing the environment, let's start a new terminal. Click here and start a new terminal. And over here in the terminal, let's execute this command. This command sources the underlay. That is, it's executing this setup.bash script. And we can continue further. Now, after we create our package and compile everything, we will need to execute another source command that will create an overlay. The overlay is a configuration and a set of parameters that enables us to execute programs and nodes of the created package. The next step is to install the TurtleSim package. Most likely, if you have followed the standard installation instructions for ROS2, you will be able to install or actually automatically run TurtleSim package. However, just in case, let's try to install it. Before you install any program or any application on a Linux Ubuntu, you need to execute these two commands that are compressed as a single command. This first command is going to update the package list on your local computer, and the second command, shown over here, will upgrade all the packages. So run this command, enter your sudo or superuser password, and wait. It's going to take a while to execute this command. At a certain point you will have to press Y, and that's it. Let's see how long will it take to execute this command. I'm executing this command maybe once or twice a week, and consequently the progress will be really quick. Then to actually install the Turtle Sim simulation, you need to execute this command. Okay, let's verify the Turtle Sim is properly installed by executing this command, and the output should look like this. This command lists all the executables inside of the Turtle Sim package. For us, the most important application is Turtle Sim node. So let's start the Turtle Sim node. To do that, you simply need to execute this command, ROS2 run Turtle Sim. This is the name of the package and then the name of the executable. And if you execute this command, you will see this cute turtle over here, and this turtle will be the model of our mobile robot. If you now press Ctrl C over here, the window will disappear and you can try to run this command and you will see another turtle. So my suggestion is to try to run several commands in order to see a nice green turtle. I mean, this one might not be bad. However, let me run a few times. Yeah, this one is good. Okay, we are going to play with this turtle. Remember not to close this Turtle Sim window, that is, keep it open throughout this tutorial. And to do that, make sure that this terminal is not closed. Our Turtle Sim simulation is a 2D model of a mobile robot. We can control the position of this robot by sending the linear velocity and angular velocity commands. These commands will be sent through an appropriate topic. We need to find out the topic name. To find out the topic name, and in order to obtain more information about the simulation, let's open a new terminal by clicking here, and then let's again create an underlay by executing this command. And let's list all the topics. Here are the topics. These three topics are associated with the Turtle Sim node. For those of you who are not familiar with topics, in ROS2 programming environment, topics are communication channels that are used to send information, or better to say messages, or to communicate messages between nodes. So what are the nodes? Nodes are actually ROS2 programs. That is, in our case, this simulation is a node. The simulation can receive certain commands and send some additional information to other ROS2 programs. So let's see the topic that's used to communicate information to this simulation. This is the name of the topic. Command velocity, as the name suggests, are command velocities. Let's obtain more information about command velocity, and to do that, let's run this. This command will list additional information about a particular topic. In our case, this is the topic name. We can see the type of messages that are being sent through this topic. They're of the type geometry message, dot message, twist. That is, we are sending twist messages to our simulation, or better to say, our simulation is expected to receive the messages of the type twist. In robotics, a twist is a six-dimensional vector composed of linear and angular velocity vectors. That is, to control this robot, we are going to send desired linear and angular velocity for our turtle. The linear velocity is the simple velocity that enables turtle to move in its local x-axis. That is, we can move the turtle straight. To change the direction of motion, we need to send the angular velocity vector, and the angular velocity vector will make the turtle spinning, that is, rotating. And these 6 components are embedded inside of the twist data structure, or better to say, twist class. This is very important for writing a C++ and Python codes. Then we can see that there are no publishers to our topic. This is because we didn't implement our node, and there is only a single subscriber, and this single subscriber is this particular turtle sim node. This is very, very important to keep in mind. Next, let's confirm that twist is actually a 6-dimensional vector. To do that, we need to execute this command. By executing this command, you can see that the twist message is split into linear velocity vector with its 3 components or 3 projections on the x, y, and z axis, and the angular velocity components with its projections on the x, y, and z axis. Later on, that is in the sequel, we are going to explain how these axes are being formed, and we are going to explain how to derive the control algorithm. Here, it's very important to keep in mind that we are going to only control x component and the z component. That is, we are going to control the x component of the linear velocity and the z component of the angular velocity. And the reason for this will be explained in the sequel. In the sequel, we will explain the kinematics of a mobile robot, and we will derive the control algorithm. Over here, you can see an illustration of a mobile robot in the 2-dimensional plane. Here are the wheels. This is the first wheel, and this is the second wheel, and here is the robot body. The point B is the point associated with the center of the robot. This can, for example, be a center of the mass or a purely geometrical center of the robot. In this particular case, we have selected a differential drive configuration. However, everything explained in this video tutorial with slight modifications can be generalized to other geometries and to other actuation mechanisms. The point D is the desired point. However, before we derive the control algorithm, let us introduce coordinate systems. Coordinate systems are also known as coordinate frames or simply frames in the robotics literature. As mentioned previously, let the center of the robot be denoted by the point B. At the same time, this point is the origin of the body coordinate system B. So let's explain what is the body coordinate system and what are the axes of the body coordinate system. The axis of the body coordinate systems are xb. Let me zoom in. Here it is. Here is the xb axis and the yb axis. This coordinate system is fixed to the robot body and moves together with the robot. In addition to the body coordinate system, we also have a base or fixed coordinate system shown over here. The origin of this coordinate system is denoted by O. This is a fixed coordinate system with the axis, as mentioned previously, denoted by X and Y. The center of the robot B has coordinates X and Y in the base coordinate system. This is the position of the robot in the base coordinate system. That is, over here, you can see B, and then in parentheses, you can see X and Y. These are the coordinates of the point B, or better to say, the coordinates of the center of the robot in the coordinate system OXY. To summarize, we have two coordinate systems. We have the coordinate system XB, B, YB, and this is the so-called base coordinate system that's fixed with the robot and moves and rotates as the robot moves and rotates. And we have the XOY coordinate system, which is the fixed coordinate system. The orientation of the base coordinate system with respect to the body coordinate system is described with the rotation angle theta. Or here I need to make a correction. The orientation of the body coordinate system with respect to the base or the fixed coordinate system is denoted by this angle theta. Namely, this angle theta is the angle that this body axis is creating with the line that's always fixed horizontal line and that is parallel with the fixed axis x. Again, orientation of the robot is represented by the angle that xb creates with a line that's parallel with the base coordinate axis x. And this is the angle theta, as you can see over here. Theta dot is the angular velocity. Let the desired position of the center of the robot body be denoted by the point D. Here is the point D with the coordinates xd, yd. This point is selected by the user and this is the final destination of the robot. That is, we want to steer the robot to this position. The control objective, again, is to move the center of the robot body B to the point D. Here, we are not explicitly controlling the orientation angle theta of the robot. That is, we don't care how the robot will orient itself at this point D, we just care that the robot goes from the point B to the point D. This is achieved in practice by changing the velocities of the first and the second wheel. Namely, if you want to rotate the robot, then you're going to simply fix this wheel and then you're going to rotate this wheel over here. Or another idea is to rotate the wheels in the opposite direction and this will directly rotate the robot around the point B. We are not going to go into more details into how the wheels should be rotated. For us, the control commands will be the velocity VB and the angular velocity theta, and this will be explained in the sequel. Let's explain the kinematics of this robot. At any time instant, the robot can only move along the direction of the body coordinate system axis xb. And keep in mind, that is, at the fixed time instant, the robot can only move along the axis xb with velocity vb. We call this velocity vector as the linear velocity. Of course, since we can rotate the robot around the point B, this vector, or better to say the axis direction xb, can change from one time instant to another. However, the fixed time instant, the instantaneous velocity is always in the direction of xb. That is, we assume that we can control the linear velocity vb. Also, we assume that we can control the angular velocity of the robot body. Since the orientation angle of the robot body is denoted by theta, the angular velocity of the robot body is denoted like this, theta with a dot, where this dot notation is used to denote the first derivative. To summarize, we assume that both the linear velocity vb and the angular velocity theta dot of the robot can be controlled. The position controller should compute these values, and then these values are sent to the local controller that should move the robot and produce these velocities. When we say move the robot, this local controller should actually, on the basis of VB and theta dot, figure out how to rotate the first and the second wheel such that this motion is achieved. In this video tutorial, we are not going to explain the local controller, we are just going to explain the global controller that will make sure how to go from point B to D, that is, how to set the velocity VB and theta dot in order that the robot moves to the desired position. Of course, in practice, you will also have to worry about the local controller. Under the assumption that the position of the point B is known, that is, the coordinates x and y are known, from this triangle here, let me zoom out to see, we can observe that tan or tangents of the angle theta dot is simply equal to this distance over this distance. That is yd minus y over xd minus x. And that's precisely the tan of theta d, where theta d in this equation is referred to as the desired orientation angle. And this is very important to keep in mind. The tangents of the desired angle, that is of this angle over here, is simply this distance over this distance. And if we know the current center of the robot in the coordinate system x and y, then we can easily compute this angle by simply inverting the tan function. And you will see that later on in the code. That is, from the previous equation, we can obtain the equation over here. Note over here that a tan 2 is the inverse tan function, or better to say, a tan 2 is the second argument arctangent function. Why do we use a tan 2? Well, we are using a tan 2 in order to take into account the quadrant in which we are. Namely, if you, for example, have a positive or negative values over here, then a tan 2 will properly interpret these positive or negative values such that the angle is properly computed. And always do not use the base a tan function, use the a tan 2 or the second argument arctan function. We can always estimate, or better to say in our application, we can use a sensor associated with our turtle to obtain x and y coordinates, and we will explain that later on. So let's explain the significance of the desired angle theta d. Namely, if the orientation of the robot theta is equal to theta d, that is, if this angle theta is equal to theta d, then obviously the robot will move along this straight line, that is, along the shortest distance or the line connecting the points B and D. And this is very important. So again, if theta, that is, if the current orientation of the robot is equal to theta d, the robot will move along this straight line, and the robot will approach the point D along this line BD, that is, along the line of the shortest distance. Consequently, the simplest controller for steering the orientation angle to desired orientation angle is given over here. Let's analyze this equation and let's explain what's written over here. Theta c dot is the control signal in the form of the angular velocity, and k theta is the controller parameter selected by the user. The control signal theta c is sent to the local controller, and the local controller should produce this angular velocity. That is, by using this equation, we are going to calculate the desired angular velocity that is being sent to our controller. And this is very important. How this desired angular velocity is being computed? Well, it's simply being computed as kt, k tau better to say, which is the controller parameter selected by the user, multiplying the angle, or better to say the error angle. Theta d minus theta is the error angle. That is, this is a proportional controller for the angular velocity. Namely, if theta d is equal to theta, then this term is equal to 0. And since k tau value doesn't matter, theta c dot is equal to 0. That is, if we are moving along this straight line, we are not going to set any angular velocity. That is, theta c dot will be equal to 0, and the robot will not rotate anymore since we are moving along the desired direction. And this is very, very important. On the other hand, if this value is positive or negative, then we are going to change the angular velocity such that we make this difference equal to 0. That is, such that we approach this line over here. and this is very important. And this is the first control equation. Now that we know how to control the orientation, let's learn how to derive the control algorithm for the velocity VB. So let's think logically. We can design a controller for velocity that will react or that will depend on the distance from the point B to the point D. Obviously, from simple geometry, it follows that the distance from the point B to the point D is given by this equation. That is, we are simply going to compute the hypotenuses of this triangle, and then we are going to use Pythagoras theorem. We can see xd minus x squared, yd minus y squared, and if we take a square root, we are going to get the distance from B and D. And this is the error for our control algorithm. And consequently, the linear velocity controller is given by this equation. It's simply kv, where kv is the parameter selected by the user multiplying the distance. Let's analyze this algorithm. If this value over here is non-zero, let me just show you the value. That is this value under the root. That is, if the distance is non-zero, we need to adjust the velocity. That is, we need to move, right? And kv is the proportionality between the velocity and the distance. On the other hand, if the distance is zero, this means that we have arrived at this point and we don't need to move the robot, and consequently the velocity of the robot will be equal to zero. And this is very, very, very important. Now, we can easily summarize our two control equations. Here they are. Or better to say, three control equations. At every time instant at t, we assume that we can measure the current position of the center of the robot. That is, we assume that x and y can be measured. Then, the user sets the coordinates of the desired location. That is the coordinates of the point B, D, actually of the point D, given by xd and yd. Then, at every time instant, we can compute the desired angle. The desired angle is basically the desired orientation of our robot. That will make sure that the robot moves along the straight line from the point B to the point D. Then, on the basis of theta d, we can compute the desired angular velocity. That is, we are going to compute the angular velocity. This angular velocity will always try to steer the robot toward the line BD, and then we can also compute the velocity VC. And that's it. Simple as that. These three equations constitute the control algorithm. Note over here that the control algorithm is in the form of the proportional controller. This is because theta c and vc depend proportionally on the error quantities. Of course, you can modify this control algorithm to introduce integral action and to introduce derivative action, or you can even design a model predictive controller or something similar. Now that we understand the kinematics of the robot, and now that we have derived the control algorithm, we can proceed further and create a ROS2 Python package and node for controlling the position. Here we need to perform the following steps. Number 1, we need to source the environment and create the workspace folder. Number 2, we have to create an empty package folder structure and required files. Number 3, we need to implement the source file of the controller. And number 4, we need to modify the configuration files. Later on, we need to build everything and to run the controller. So let's go step by step. First of all, open a new terminal. In this new terminal, create an underlay by sourcing setup.bash file, then make sure that you're in the home folder by running this command. Then create a workspace folder, and inside of that folder create the source folder. To do that, we use this command. The name of the workspace folder is given over here, and the name of the source folder is src. Next, we need to navigate to the source folder. To do that, you need to execute this command, And now you're in the source folder. Inside of the source folder, we need to create an empty package structure. That is, we need to create a template for our package. To do that, we execute ROS2 package create, then we specify the build type, which is amend Python, and then we specify the name of the package. Here, the name of the package will be pospy package, which stands for position Python package. And let's press enter. Now, you will see that certain files and folders are being created. First of all, you will notice that inside of this folder, there is another folder whose name is equal or identical to the package name. So let's go to that folder, and inside you have several files. Let's briefly go over these files. Package.xml and setup.py are configuration files. Then you have additional folder called resource and test folder. These folders will not be used in this video tutorial, and for us the most important folder is the folder whose name is identical to the name of the package. So let's navigate to this folder. This folder contains or should contain Python executable files or the Python files of our package. And here we will implement our controller. First of all, you can use any Python editor to create the file. In my case, I'm going to use Visual Studio Code. If you don't have Visual Studio Code and you would like to install Visual Studio Code on a Linux Ubuntu computer, then go to my YouTube page. There is a tutorial on how to install Visual Studio Code on Linux Ubuntu. Simply search for Visual Studio Code Linux Ubuntu and there are several tutorials. So let's start Visual Studio Code. Here it is. Okay, and let's create the file. Click on File, New File, and call the file as demo.py. Here it is. Save it inside of this folder, and let's proceed. Here, to save time, I'm going to simply paste the content of the file, and I'm going to explain this file line by line. Also, over here, you can see that I have added a significant number of comments, and my suggestion to everyone is to thoroughly comment your code, since you don't know who is going to read your code or who will later on work on your code. First of all, we need to import the necessary packages, classes, libraries, and modules. On the code line 6, we are importing RCLPY. RCLPY is the ROS2 client library for Python that is included with any standard installation of a ROS2 distribution. RCLPY provides the standard application programming interface for using ROS2 in Python. Then, from rclpy.node, we need to import node. A node class is the main class of RCLPY that implements the basic ROS2 node functionality. That is, inside of the ROS2 world, everything is object-oriented. If you want to create a ROS2 program, then you're going to start with the standard template class, which is called node, and you're going to modify this class. The mechanism for modification is inheritance. That is, you're going to define or declare your own class that inherits the methods, functions, and the member variables from node, and that's the main idea. Then, from geometry messages.message, we are importing twist. Namely, everything in the ROS2 world is structured as messages. For example, command velocities, poses, images, text, floats are messages. In our case, we are importing the twist class. Twist class is a class containing components of the linear and angular velocity vectors that are used to control the 2D mobile robot. This message should be sent through the topic turtle1 command velocity. And note over here that this topic is exactly the topic that we found over here. And this name in our code should be exactly this one, as you will see later on. Then we need to import pose. Again, A pose is a type of the message from the turtlesim.message. Pose is a class which contains the information about the position, orientation, linear velocity, and angular velocity of the 2D robot. To explain this, we are going to use pose to read information about the position and velocities of this robot. That is, these are sensor messages. We assume that there is a sensor attached to this turtle, and this sensor measures the position and the velocities as well as the orientation, not to forget this, of this turtle. These messages will be sent through an appropriate topic, and the name of the topic is Turtle1 Pose. It's given over here. Turtle1 Pose is not the name we invented. Turtle1 Pose is the name we retrieved by running this command. That is, our node, that is our turtle sim, has a standard topic name that's used to communicate sensor messages. The sensor messages are in the form of a pose data structure. The pose data structure contains information about the position, x, y, and the position, again, keep in mind, is given with respect to the coordinate system, which is in this case oriented and positioned over here. That is in this coordinate. Then it also gives information about orientation. That is, the next component of pose is the orientation. Then the two additional components are linear velocity and angular velocity. That is, pose gives us the complete information about the kinematics and position of our turtle, as well as the orientation in the corresponding coordinate systems. Here are the topic names. Topic 1 is the topic for sending control velocities or for controlling the turtle, and topic 2 is the topic for receiving sensor information. Next, we need to import time and math for tracking time and for math functions. This class over here implements the control algorithm. This class is inherited from the node class, namely, after class name, we specify in parentheses node. This means that our class is inherited from the base node class. And if you go up, you will see that the base node class is imported over here. Next, we need to specify, or better to say, to define a constructor. In the object-oriented programming, once the object is created, a constructor is being called. The constructor is a special function that will set and reserve the memory space for our object, and that will perform all the initialization and all the definitions, as well as assign the values. However, inside of this constructor, we need to call the constructor of the base class, and we do it over here. We call explicitly the constructor of the base class by using the super function, and we specify over here the node name. That is, our node will be called controlled node. Next, we need to explain what our constructor is receiving from the user. We're receiving xdu and ydu. These are the xd and yd coordinates of the desired point. U means user. That is, xdu and ydu are set by the users. Then we have the kvu and k theta u. These are the parameters, that is the proportional gains of our controller. Keep in mind that. Here, we store these values inside of our class. And then over here, we instantiate or create the message. The last received message will store the sensor information. And this sensor information will be periodically updated during the operation of the code. It is of the type pose, and consequently I'm calling the constructor of the pose class. Again, pose contains the sensor information, that is the position, orientation, and velocities of our robot. Then we need to measure the initial time, and we are always going to refer to this initial time, that is relative to this initial time. Then we need to create the timestamp when self-receive message is updated. Later on in a function, we are going to update the pose, and we are going to update this timestamp of the pose. That is, the last received message time is the timestamp of the pose message. Then we need to instantiate the twist object. Self.control velocity is of the type twist, and this is the value that our controller is going to calculate. Then we need to initialize the values. We set all the values to 0. And to explain this further, the control velocity, which is of the type twist, has 2 components. Every component has 3 additional components. Linear is actually linear velocity vector. Linear velocity vector has x, y, and z component. Similarly, angular is the angular velocity vector. It also contains 3 components, x, y, and z. Next, we need to create a control publisher. A control publisher is an object that governs publishing on messages. Messages that we are going to publish are command velocities, which are of the type twist. They're going to be communicated to the topic 1. Where is topic 1? Here is the topic 1. That is, the topic 1 is the topic that our node, that is our simulation node, is continuously listening. And we are going to send twists to topic 1, and 10 is the buffer size. Similarly, to receive the sensor information from our robot, we need to create a publisher object. Here, the type of the messages that are being transmitted are of the type pose. They're being communicated through the topic 2. Where is the topic 2? It is over here. And then here comes magic. We need to specify the name of the function or the name of the callback function that will be called every time there is a message on topic 2. That is, every time our node, or better to say TurtleSim, sends through the topic called topic 2 a message of the type pose. When this thing happens, a function will be called. This function is a sensor callback function. Next, we need to define the period of the control algorithm. That is, we need to specify how often control messages are being sent by the publisher. Over here, I'm specifying 0.250. That is, every 250 milliseconds or 4 times per second, I'm going to send control messages. Next, we need to create a timer object that will enforce this communication frequency. The timer object is created like this. I need to specify the period, and I need to specify the name of the control function. The name of the control function is the function that will calculate and send control actions. Okay, so let's explain first of all the sensor callback function. Sensor callback function is referred over here, and its purpose is to receive sensor information. That is, at every time instant or some local operating system time instant, our TurtleSim simulation sends messages of the type pose. That is, it sends position, orientation, and velocities to an appropriate topic. Then this function makes sure that these variables, or better say the pose, is stored in the last received message. And then over here we are also recording the timestamp. That is when the message is being received. Here is the control function. The control function is used by our timer, and this control function is called with a period of 0.250 seconds. That is, 4 times per second we are calling this control function. This control function will calculate the values of control. It will calculate control values. So let's see what's happening inside. First of all, this comma here is completely unnecessary, so let me save this in order to correct my code, since none of the messages is explicitly passed to control function. This control function, since it is a member of the class, can receive the private member variables of the class, or it can see them. it basically reads the x and y components as well as the theta component from the pose. That is our last received message, has x, y, theta as well as the velocity fields. However, we are only extracting x, y, and theta. And over here, we are implementing our equations for the controller. First of all, we are calculating the desired orientation. And for that purpose, it is instructive to bring up the control equations. Let me now zoom in here. Let me do this so you can see them. And you can see nice implementation over here. First of all, theta d is the equation number 6. Then, line over here, that is this line over here, is our velocity, is the equation number 8. And this equation over here, that is the theta velocity, is actually the equation number 7. And that's it. Simple as that. Now, once we calculate x velocity, we need to fill in the fields of the control velocity. The control velocity is of the type twist, and we need to fill in everything. Since we are only controlling the velocity in the local x-axis or in the axis of the body coordinate system, we set x velocity here for the x component, 0 and 0 for the y and z component. Then for the angular velocity, we set 0 for the x, y should be 0, and theta velocity should be the z component. The z component is actually the component of velocity that's perpendicular to our screen. That is, in kinematics and in mechanics, the velocity theta dot is projected on the axis that points from the screen toward you, and that's your z-axis. Then we are simply printing, sending the control commands. Then over here we are publishing the control message, then we are printing them on the screen, we calculate the time, and we simply print the values. And that's it. That's our class. Okay, and finally here is our main function. Before using the RCLPY, we need to call the init function. The init function is called like this. Then over here the user selects the control parameters, proportional gains for velocity, as well as the coordinates of the desired point. Over here we are creating the node, we are starting the node by using the spin function, and over here we are destroying the node. Note over here that this is a blocking statement. That is, once this statement is executed, the code will stop here, or better to say, the node will be continuously executed. Once you press Ctrl C, destroy node and shutdown will be executed. And finally, here is our main. If name main, this is the entry point. Okay, let's save this code and let's continue further with the implementation. Besides implementing the control algorithm inside of the file called demo.py, we also need to add 2 additional configuration files. Namely, if you go back to the terminal and if you go one step back, you will see the file package.xml and setup.py. These are the configuration files that we need to edit. So let's start with the package.xml. Click on File, then click on Open File, then go here, and then click on package.xml. And over here, you need to enter the dependencies. So what are the dependencies? If you go back to the Python file, and if you go all the way up, you will see that we have these import and from statements. That is, our code or our Python file depends on additional modules and libraries as well as classes inside of the standard and non-standard ROS2 packages. The standard package is RCLPY, then geometry message and turtle sim. Over here, if you have some other packages that you're defining, then these will be non-standard or user-defined packages. However, although our code only depends on a built-in ROS2 packages, we need to set or define what are the dependencies. And to save time, I need to enter these lines over here. So let me do it here. And now we are saying to ROS build system that our Python file should depend on RCLPY, geometry messages, and turtle sim. So let's save this file. The next step is to edit the setup.py file. Click on File, then open it. And over here we need to set the entry points. What are the entry points? Namely, we are going to run the code like this. We are going to open a window, source the environment, and then we are going to type ROS2 run, then the name of the package, which in our case will be like this, and then over here we need to specify name of executable. Here, instead of this general parameter name of executable, we need to define or specify the executable file. However, we need to tell to the build system what is the name of our executable. And for that purpose, we need to define entry points. We need to define the name as well as how to start demo.py file. So let's edit this field. Here I need to copy this. And then here I need to paste this part. Let me now nicely organize it so you can see what's happening. Here it is. Let me do it like this, and then let me close this so you can see what's happening. Okay, so the entry point, then you need to specify this parameter console script, and then here's the name of the executable. It will be publisher. That is, once the user here writes something like this, publisher, the system will know to look into the post.py package, that is to look into our package, to find the file called demo.py, and inside of that file to execute the main function. And that's precisely what's written over here. Let's save this file and let's continue further. Now, save this one, and save this one, then go back to the terminal, go over here, then go one step back, then another step back, and make sure that you're in the base folder. Inside of this folder, we need to build the package. However, before we build the package, we need to install ROS2. ROS2 is a very useful tool for making sure that all the dependencies are properly installed. Let's run this command to install ROS2, and then let's initialize ROS2, and then let's update ROS2. Next, we need to verify that all ROS2 dependencies are properly installed. For that purpose, let's again make sure that we are in the base folder and then run this command. And if everything is properly installed, you should see this message, all required dependencies installed successfully, and then we can run the package, or actually we can build the package. To build the package, make sure that you execute this command. You're calling callback build, then you're selecting the package, and then you're specifying the package name. Note over here that you can run this command simply by callback build, since we have only a single package. The advantage of this approach is that you can actually specify a package that you want to build. If you don't specify this parameter, all the packages are built. So imagine you have thousands of packages, then this callback build will take forever. This way we are only building a single package, and if everything is properly being set, you should not see any error, and we can proceed with execution of our code. To execute our code, first of all, make sure that this terminal here is open. That is, that our ROS2 turtle sim simulation is running. Then I'm going to close this terminal. Keep this terminal open. That is the terminal which you build. Open a new terminal. Then create an overlay. To create an overlay, we need to execute setup.bash file inside of the installation folder and inside of our workspace folder. That is, we are executing setup.bash not from the base ROS2 folder, but from the base folder and the installation folder of our created package. And now you can run your publisher. To run the publisher, you simply need to type ROS2 run, then the name of the package we created and the name of the executable, which matches the name of the executable in the entry point file. And then over here, let's open this terminal and let's watch and let's see what happens. Now if you press enter, here it is, we are moving our turtle. And over here you can see where we are moving. We are moving to the position 0.5 and 0.5, and that's precisely this position over here. Simple as that. You can of course play with these commands over here and you can go anywhere else. However, make sure over here that 00 coordinates are noted, are actually 00 origin is located over here. Of course, now code is running and you can see that we have reached our destination, and then you can see finally that theta angle is set to 0. Okay, that's all for today and thanks for watching.